I am essential from electronics engineering.
Just speak up. Speak up.
So,
You can take off your mask. Then present.
thank you, Professor. So I am essential from electronics engineering department, and my advisor is Professor J.M. Parks. Today I will present development of ultra-high output dielectric electromagnetic biomechanical energy harvester for wearable cell power sensor and smart electronics. So here is my research outline. So I will discuss my research motivation and review of previous work and some challenges. Therefore, so I developed multi-layer dielectric nanogenerator, nanofiber-based dielectric nanogenerator, and biomechanical hybrid energy harvester. Finally, I will discuss summary and future work and also my research achievement. So, smart wearable electronic have received significant research interest in various fields like e-skin application, robotics, virtual gaming, industrial application, and automobile application. However, so all electronic devices and sensors require external power source that increase complexity because of short lifetime and limited periodic charging and inconvenient to replace and also environmental hazard. So to solve this problem nowadays, renewable energy source is most important because of is available from environment and pollution free. So among them, my choice is biomechanical energy harvester because biomechanical energy harvester is wide application and it's integrated with human, and also large power density we can achieve from this biomechanical energy harvesting. So that's why I choose biomechanical energy harvesting. So in case of previous work, so basically in case of TNG, so they focus four type of mode, and among them, so different groups reported different type of works. For example, this group reported magazine and PVA composite to increase the output performance. So also this is another group, they work PDMS and magazine to composite material to improve the output performance. However, as you can see, the power is not too much improved. And similarly, so different group reported different layer to improve the output performance. So here you can see some group reported nanofiber based work, multi-layer TNG to improve the output performance. However, as you can see the figure, output performance is not improved, like 0.15 watt per meter square. And also they use intermediate layer to improve the output performance, another group. So also output performance is not too much improved. So therefore, so in case of TNG, as a cell power sensor it works. So some group reported surface modification to improve the output performance. Here as you can see the dome shape structure to improve the surface modification output performance, but sensitivity is like small, 150 milliwatt per Pascal. So some group use nanofiber based work, that also nanofiber improve the surface area, and also this is also nanofiber based work. They use magazine and PVA to improve the output performance. However, this performance is also little bit improved, but not too much, about around milliwatt. So these are the previous work. So among them, also hybrid, I work hybrid energy harvester. So previous work here is, as you can see, the TNG and DMG use. So rotational type of device they make, and performance is still low, like a few milliwatt, 10 to 50 milliwatt. And this is also EMG and TNG based hybrid energy harvester. This is also rotational based, and this is like battery type hybrid energy harvester. This included TNG, EMG, and TNG. So output performance is like microwatts, so not too much improved. So that's why our main concern. So some challenges still we have, like high power density and fast charging, also high sensitivity, variability and high stability and humidity resistance, and also stability. So there are many challenges. So to solve this problem, so my approach is I did 6 works, like contact lens double layer TNG, stretchable humidity resistant TNG, magazine nano composite based TNG, and connected function like composite TNG. That's are included in nanofiber based work. And finally, I did hand motion driven hybrid generator and human body induced vibration with nanogenerator. Those are goes to hybrid nanogenerator. So first I will discuss multi-layer based cybernetic nanogenerator that is compared with W actually. So in this case, in this COVID situation, contactless is very important. That's why my target is contactless TNG. So in this case, I developed cobalt NPC as a new composite material with EcoFlex, and that I use as a charge generating layer. And also I use magazine and EcoFlex as a charge trapping layer. So this approach I use flexible fabrics as a electrode. By using this technique, so this is the fabrication method. So I make 3D printed mask to control the thickness. After that, I attach sandpaper to create micro structure that also increase the output performance. And after that, I make two cobalt NPC and EcoFlex composite, and finally I make magazine and EcoFlex composite as a charge strapping layer, and I use electrode in this case fabrics electrode that is flexible, and I make double layer TNG. So cobalt NPC, we prepare carbonization method. By using this method, we make cobalt NPC. This is the FPCM image, and after that, we mix with EcoFlex as a composite material, and we make microstructure by using sandpaper assisted. We increase the electric contact area, and this is the extract analysis, the crystallization, and also working principle. So as you know, the TNG works on contact electrification and electrostatic integration. That is basic principle. So after that, so most important thing is optimization of the nanofiller. So I characterized dielectric measurement with different filler materials. So successfully I measure 1% shows the highest dielectric constant because of after adding some filler is create microcapacitor formation that increase the dielectric constant, and which is verified by output measurement, also electrical analysis, and this result is verified by surface potential. We have electrostatic voltmeter that we can measure surface potential, and I optimize so different kind of material like pure EcoFlex, and after that I did DRF67 and cobalt NPC, and I found that so cobalt NPC and EcoFlex shows the highest output performance. Similarly, so single layer, as I mentioned, so I use double layer. So I compare single layer and double layer. So double layer shows the highest output performance. This result is also verified by surface potential. So nowadays, contactless TNG is most important thing is charge decay time. So our device shows the highest slow charge decay time. That's why it can get more charge and it works well. These are the result, and so friction different kind of material I have tested. Among the human skin shows the highest output performance because our device is highly negative and human skin is high positive. That's why human skin shows highest output performance. So thickness is important fact in case of TNG. So that's why I measure different kind of thickness performance. So among them, 1 millimeter shows the highest performance because low thickness it creates charge leakage. That's why it reduces the output performance. And after also if we make high thickness device, then it will create increased resistance that will also reduce output performance. So in case our target application is human biomechanical energy, so it's less than 5 watts. So that's why we measure frequency around 5 watts. And so as I mentioned, so our contactless work, so that's why distance is important fact. That's why we measure different distance. Our device capable to detect up to 20 centimeter distance. And based on this distance, we can use our device as a human motion monitoring. And also carbon obstacle detection, our sensor also work. Here is some demonstration as you can see. So during the session, we can realize our device by using our device. So also robotic application, so friction is very important. That's why our device also can detect robotic obstacle detection. Here as you can see the figure, and this is the also based on our device we make array or non-contact password authentication system, and as you can see the demonstration. So our sensor can detect password authentication without touching. So because of COVID situation, it also works in the application. So therefore, so my research is second research is like stressable humidity resistance TNC. My focus is this TNC is not stressable, so stressable and humidity resistance, so environment friendly. That's why my plan is, so I make multi-layer TNC. So here I approach 5 approach. So I develop MF 525. So this MF is better stability as compared to cobalt NPC. So that's why I use as a charge generating layer, and I develop hybridized nanocomposite that is consist of cobalt NPC, magnesium and ecoflex as a intermediate layer, bifunctional intermediate layer. At a time it works two functions, charge trapping and charge transport. So therefore I use in this work I use flexible electrode, also which is conductive and also stretchable. And another approach is I use 3D printed microstructure, that is also increase novel work, this one that increase the output performance. And finally I encapsulate it with ecoflex. That's why it can save humidity resistance clearly. So this is the fabrication procedure. As I mentioned before, similar. We make 3D printed, but this time we have microstructure in this template to create surface modification. And this is the working principle, so same as like before, it works on contact electrification and electrostatic induction. So we did console simulation, so optimize the device performance. And therefore, here is the basic charge trapping mechanism why I use bifunctional intermediate layer. In case of this figure, as you can see, the first row, so its charge combination is very high without high bifunctional intermediate layer. But in figure 3, after using bifunctional intermediate layer, it can trap charge and reduce charge combination. This result is also verified by surface potential. So as you can see this figure, so there are ecoflex and multi-layer TNG. So multi-layer TNG show the high surface potential, and this performance is very stable, not surface potential not reduced. That's why our approach is good. And based on this principle, so initially we prepared MF 525 by using submethylone method, and this is the efficient image of MF 525, and this result is also verified by the EDS analysis and also XRT analysis, the crystallization of MF 525. So similarly, so performance optimization is one of the important fact. That's why we mixed MF 525 with ecoflex different white ratio and measure the output performance as relative permittivity. As you can see, the 1.5% shows the highest output performance, relative permittivity, and this is similar to surface potential. And also we measure output electrical characterization, that is show the similar trend, and also we measure the power. So peak power also 1.5% shows the maximum peak power. Based on this, so another approach is for hybridized intermediate layer. We mixed cobalt NPC and magnesium with ecoflex, and this is the nanofiller. So hybridized nanofiller will make this time, and this result is also verified by EDS analysis and crystallization analysis with DXRT. So also we mixed with ecoflex, this hybrid nanofiller, and we measure the electric constant. In this case, 4% shows the maximum output performance. After adding this nanofiller, it creates microcapacitor formation that increase the capacitance, then output performance increase. So after certain portion like 4% is performance reduced because of calculation method. So this result is also verified by surface potential and power. So all those results related to 4% shows the high output performance. So this application also will focus basically biomechanical energy. So therefore we measure the frequency of change, the output voltage is almost linearly increased up to 6 Hz, and force. So we measure the force different situation. So up to 16 newton, it shows the output performance increase. After 20 up to 10 neutral is shows the linear increase. After that it's saturated because after high force, so it's achieve the maximum contact area. That's why output part is saturated. So we also measure the sensitivity analysis. So our device has high sensitivity around 49 volt per kilopascal. So as I mentioned before, so some millivolt per pascal. So our device shows the highest output sensitivity. And also our device is humidity resistant. So we test different humid condition, and our device shows the highest stable output performance. So also we did water test. So our device image on water and measure the output performance before and after. So our device is, as I mentioned, so we make eco text to protective layer. That's why the output performance is also stable. So here is the output power. So our device has highest output power around 25.7 watt per meter square. So as I assume, my goal is achieved. So stability also up to 20 K cycles, so output performance is stable. So this is the achievement. And so stressability is also important fact. So therefore we measure mechanical properties like stress is up to 245% stress, and based on this we measure different mechanical information like bending, folding and twisting. So it also shows the highest response. So based on this stability, stretchability, so our device can be attached different part of human body, like as you can see figure D, arm, elbow, wrist and finger, and also different part of body to measure biomechanical biomotion. So based on this device, our sensor can detect finger bending, wrist bending, and elbow bending, knee bending, and also we can attach our device insole application that can detect human motion monitoring system. So also this work we can use as a tactile sensor, handwriting recognition. We can use here different data we can detect by using our sensor, and the sensitivity accuracy is around 97.7%. So accuracy is also good. And based on this the device architecture, we can make different array. So we can use as a say for touch sensor and also virtual reality control application. We can use here. You can see the car monitoring near application and some tactile application we demonstrate. Therefore, another approach is we focus nanofiber based work to improve the RTH output performance. Here, this approach I use Maxit as a nanocomposite with PVD TRFE to improve the output performance.
So you need to finish within 10 minutes. So just keep important results you achieve with all the details within 10 minutes.
So this work, so I focus basically PVD, TRFE and Maxit, and I use nylon as a positive material and carbon as a spring. So that's why it's work is stability and a high output performance. So this is the nanofiber we make by using electric spinning technique. And device application and one principle is similar to device, and we make simulation for to control the air gap. And here is the XRD analysis of Maxit. So in this work, here is the experimental setup. So also similarly, we make dielectric different white ratio, and we use our white ratio and electrical characterization. And also nanofiber thickness is important. So we use a nanofiber thickness and different electrical output performance. And those nanofiber thickness we can control by using electric spinning time. So based on this frequency, so we will increase frequency, that charge accumulation increase, that output performance will linearly increase. And after that, force also we optimize, so if we increase force, the charge accumulation is increased, that's why output performance increase. And it's in case our device shows the highest output performance around 4 watt per meter square. So based on this, this device has highest stability case we did around 2 K cycles show the stable performance. So after that, we use rectified circuit to charge the different type of capacitor, and based on this capacitor charge, we can demonstrate like stepwise charging demonstration. And also our device capable to as a set power source to control electronics and device applications. So as you can see in the demonstration. So next work is based on this another approach. So in this case, I focus most of the researchers focus negative dielectric material. Here I focus positive dielectric material. So I use polydiamond as a and nylon composite material to improve the TNG performance. Here I use around 9 Kapton spring to increase the output performance, and also is like as a spring. So stability is higher than previous work, and also output performance is higher. So in this case also use nanofiber. So two types of nanofiber like nylon element and polydiamond composite nanofiber, and also PBDFT nanofiber. And also working principle and simulation I did as well. So in this case, so nylon also has mechanical analysis I did, so its traceable is better than the pure nylon. And then I did the dielectric optimization, and this is the calculation theory. As you can see, after addition of polydiamond, it increase the charge, induced charge up to certain portion. After that, it reduce because of subconductive path. And also I compared the different type of film and composite material that our device, our composite shows the highest output performance. And this is the frequency analysis, and charge is almost high. So based on this, power is also our device shows the highest power, around 2.4 milliwatt power, and stability is also up to 7 K shows the highest stable performance. And also our device sensitivity is 1.1 volt per kilopascal, so it is also high sensitivity. Based on this device, we can put our ISO application that is also can monitor different type of working condition like working, fast working, jogging, running, and everything. So this kind of human motion we can by using this system we can real-time monitoring by using our smartphone apps. Here, as you can see. So in this demonstration, we can see the motion monitoring. So another approach is biomechanical hybrid energy harvester. So in this case, I focus hand motion driven hybrid energy network. So in this work, I mainly focus harvest magnetic array to improve the output performance, and I use in case of TNG, I use a new method, that is phase inversion method, to improve the output performance. And after that hybridize, I got the maximum output performance. Here, PTAP nanostructure I made, and this is the phase inversion technique I did for TNG. And my target is portable electronics application. This is the working principle, so everyone is known. And in this work, so I use 3D simulation. So basically here you can see, so have campus magnet arrays, is path direction is one side, and that's why we can capture maximum flux and output performance will be maximum. And alternative magnetic array is axis two side, and also flux density is very low. So I made simulation to optimize the flux density around different distance, and also in this case of TNT, so I thickness is also I can simulate for optimization. So this is the parameter of simulation, and this is the TNT simulation. So this is the fabrication. So in this case, I make 3D printed computer mouse to make this device, and finally I successfully made 3D printed computer mouse with hybrid device. So this is the experimental setup. So performance, in case of performance, I compare different type of thing, and I show the phase inversion technique show the highest output performance, and also power density is without Halbus array is very low, and Halbus array shows the highest output performance. So I optimize the frequency. Our device shows 6 Hz is the highest frequency. 6 Hz frequency shows the highest maximum output performance. In the acceleration is almost 2G shows the highest output performance. So this is the performance. So in case of our hand motion, so different type of motion we can detect, like horizontal, vertical, and like diagonal, different kind of motion we can detect. So based on this TNG performance, so TNG shows the 0.2 milliwatt volt, and EMG shows 182 milliwatt power, and also hybridize. After hybridizing, so it shows 182.1 milliwatt power. So highest output power. So different motion distance also will calculate output performance. So in case of horizontal, output performance is high because it cut the maximum flux. So different acceleration. So we measure the human motion, and after that, we for a practical application acceleration we measure different type of motion like vertical, circular, diagonal, and horizontal. So horizontal this shows the maximum acceleration and also output performance because of which can power maximum flux. So this is the circuit diagram. So for capacitor charging, so ammeter is after as you know EMG has EMG has different load resistance. To optimize this, we make a transformer. After that, we use rectifier to charge the capacitor voltage. And here you can see the EMG voltage is high, but charging is slow, and EMG is charge is fast. And after the hybridizing, is charging rate is improved. That is our mechanism to improve hybridized nano generator. So stability we test for in case of PNG. Here is by using our device, you can see as you can see the demonstration. So you can charge LED. And also after that, so practical application we use our custom made power management circuit for device different kind of portable electronic device charging. So our device can able to charge smartphone and smart hygrometer and also smartwatch, and also can demonstrate cell power mouse also can demonstrate. Here is as you can see the our device can charge smartphone, so our device has highest output performance. So next work is I will basically focus so body induced vibration, that is more challenge, and also this is in this case I use also Halbus magnet array and circular magnet. So and also in case of PG I use metal material PU nanofiber. So that's also after hybridizing. So two type of PG we use this friction, utilize this magnet friction. So in this case for this approach I use PTFE as an activative material, and PU that is new material I have also here to improve the PG performance. And this is the device fabrication procedure, and this is the working principle as everyone knows. And I did APM simulation for optimization, and also here you can see the I make 3D simulation to optimize the magnet and coil position and distance and how much distance. After optimization, I make this device. So this is the simulation parameter, and this is the experimental setup. So spring is another important factor to optimize. So in this case, I optimize different. I use different spring to optimize the spring stiffness. So our device 85 Newton per meter shows the highest output performance, and frequency, different kind of frequency and acceleration I optimize by electrical acceleration. So 1.5 shows the highest output performance, and resonance frequency is around 6 Hz frequency. Our device shows the highest output performance, and stability is also our device is good stable output performance. So in case of PNG1, I got around 3.8 milliwatt power. In case of PNG2, so different peak power was 6.7 milliwatt power, and EMG was also good with in this case high. I got high output power around 1.09 watt. So after hybridization, it also shows the high output performance. And so based on this performance, I basically focus biomechanical energy harvesting. So different type of like walking, running, hiking, mounting, and handshaking. So I use in this case lithium-ion battery to charge this battery. Here as you can see the different type of charging performance. Based on this performance, our device can demonstrate smartphone charging, smartwatch charging, and Samsung Watch live charging. So also in this work I got high output performance. Therefore I fabricate sensor for EMG sensor, and after that this is the system architecture of cell power wireless system. So basically in this case I use our device as a power source to monitor the monitoring sensor application. So here is you can see the head cam monitoring system. So our device can operate this whole system. And last one is our sensor also we can use as a motion sensor. In this case, TNG I use as a sensor, and other TNG and ENG I use as a power source. Here, as you can see, so different kind of motion like walking, running, that we can detect by the smartphone application. We can real-time monitoring. We can see, we can observe by using our sensor and also harvester. And finally, summary I will discuss. So as I mentioned, so I developed three types of generator like multi-layer and nanofiber-based one and hybridized generator. So here is some comparison I have added. So multi-layer TNG, our group I compared to different group. Our group is highest output performance like 25.7 watt per meter square, and nanofiber based was we use as a pressure sensor, so sensitivity is also high as compared to different group. So, and my third work is hybridized nanogenerator. Here as you can see, so charging performance is also high because I got highest output performance like 1 watt power. That's why it's 3.7 farad it can charge within 35 seconds. So this is the summary, and my future target is so different type of biomechanical biomedical application. So I can monitor biomedical signal by real time and also accessible device, and also my plan to make more digitized and high power device for different application like SIPA and portable electronics application. And my research achievement is I published 6 SCI journal as a first author, that is nanoenergy, advanced energy material, advanced functional material, applied material interface, nanoenergy. And also I have 2 equal contributed SCI journal publication, and also author I have more than 20 journal. And I have also been international conference as a world presenter. And thank you all.
Never have any questions?
Maybe let me start. So I guess you have shown so many works here, and I guess you did a good job. But my first question is, now you have shown 3 different projects. I mean, 3 different, like this is the nano generator, so multi-layer, and nanofiber, and biomechanical, right?
Yes, please.
But and you show all the results, but I guess still I'm a little confused. What's the motivation of each work? Because you have in the beginning you have shown that there are like challenges in previous developed nano generator, right? So charge time, or there are so many things, right? So can you briefly summarize each of your work? Which part you have improved and why you started this work?
So here, Professor.
Yeah, I know you have kind of summary there, right? But for example, first your multi-layer casual nano generator, right? So in which of challenges you are trying to improve or solve through your work, and what's your outputs there?
So here I mentioned, Professor. So here, so this work I make multi-layer TNG to improve the output performance. So basically high power density, TBT I make here 25.7